Our goal is to investigate fields and effective index or propagation constant of the waveguides. The first example is a waveguide made of two metal mirrors. The fields can be calculated from the Helmholtz equation, taking into account the boundary conditions. And for perfect metal, they are indicating that the tangential components of both the electric and magnetic fields are zero at the interface. And we consider the transverse electric polarization. The electric field has only the X component. Therefore, we use this component to solve the full field between the mirrors. Our propagation direction is all the time in z direction. With these definitions, the Helmholtz equation can be written as. Now we assume that waves can be separated in transverse and direction parallel to the propagation direction, as where EY is the transverse amplitude of the field and beta is the propagation constant along the waveguide. You can see that this resembles plane wave in free space, but the difference is the amplitude dependence in the y direction. The field also depends on time by the time phasor, but this is usually omitted in the derivations. By inserting this trial to the Helmholtz equation, we'll get this equation is the second order differential equation in y direction, and it has a general solution which can be written as with the complex functions, but sine and cosine functions can also be applied. When we insert this equation into the differential equation, we can get the dispersion relation between the transverse and propagation wave numbers. The dispersion relation is this, and it's visualized inside the waveguide by relating the wave number, propagation constant, and transverse wave number. Note that the transverse wave number is the normal component of the wave number in our previous thin film formalism involving the plane waves at the interfaces. Next, we use the boundary conditions, where the tangential component of the electric field is zero at the boundaries of the mirrors. The thickness of the waveguide is d, and at both interfaces, the x component of the field needs to be zero. Now we can use the general solution, but we can also see that the sine function is a solution to fulfill the boundary condition. The transverse wave number needs to fulfill, and further. And now we can write the full field as, and our next task is to determine the propagation constant and the effective index. And this we can solve from the dispersion relation. We shall rewrite the dispersion relation for the propagation constant. And by inserting the transverse wave number, let's remember what is the wave number in general. if we take this out from the square root and once more rewrite this part, then we can write the propagation constant as where the effective index is defined by the square root expression. Let's investigate what the propagation constant and effective index show about the propagation of waveguide modes. We'll see that the effective index depends only on the wavelength and distance of the mirrors, and it's also discrete, where m gets integer values. Let's take an example of the mirror waveguide, where the distance between the mirrors is 1000 nanometers, and we'll calculate the effective indices as a function of wavelength. We see that for different values of the integer m, we'll get different effective indices. So the first waveguide mode is obtained with an m equals to 1. Then we have mode with m 2, 3, and 4. We see that the effective index is below 1, indicating that it's smaller than the refractive index between the mirrors, if we assume the index to be air. We also see few special points where the effective index is crossing the 0, and this point is called a cutoff wavelength. At these points, the square root is negative, and let's calculate the cutoff value. And we'll see condition of cutoff is simply the distance between the mirrors is multiple of the half wavelength. So it means that for mode order 1, one half wavelength fits between the mirrors. For mode order M2, 2 half wavelengths fit between the mirrors, and so on. Often we are interested in a so-called single mode regime. It means that the dimensions and wavelengths are such that only one mode can propagate in the waveguide. And in this example, such a region is here because M is 1, mode is the only mode. And this regime is the so-called multimode regime because any selected wavelength, we have at least 2 possible modes in the waveguide. And let's next take a look, how does the field look like for different effective index values. So we have already solved the field of the TE polarized mode. And let's first select a constant effective index and observe how does the field look like. We select the index at 0.5. Now the M equals to 1 mode has a single maximum at the middle of the waveguide. This is often called as a TE0, where the subscript means that there is no zeros at the field profile. M is 2 mode, has 2 maxima. It is named as TE1 since there is 1 0 in the middle of the waveguide. Similarly, M is 3 mode, and finally M is 4 mode. Let's take a look how the fundamental or TE0 mode behaves along the wavelength values. We take the effective index values at 1000 nanometers, 1250, 1500, 1750, 2000 and beyond. And here are the field profiles of the TE0 mode. As the effective index is decreasing, the wavelength of the mode in the propagation direction is increasing all the time. And when we reach the cutoff wavelength, field is extending to infinity. The field is not propagating anymore, but it's kind of filling the full infinite waveguide. When we go to the wavelengths above the cutoff, the effective index will be complex, and therefore it's heavily attenuating in the propagation direction. So the field is not propagating, but it's evanescent. And this happens with all the modes below the cutoff wavelengths.